Hello, this is Josh Hale doing my second data structures assignment about binary search trees. So when you download the zip in the directory, you should see the main.cpp in the make file. To compile, it's as simple as make. It generates it, and then you will see that there is a executable that you can run with .bst. Running the program will generate a binary tree with the given numbers 6 through 99. And it will then say tree's been constructed, and it will ask you for the kth element that you'd like to search. So you simply put in, say, 7, and it'll say the seventh smallest element is 57. And 1, 2, 3, 4, 5, 6, 7. 57 is the kth smallest element for 7. If I'd like to run it again, it will generate the tree again, and then say I put in something like 90, it'll be element 90 is not valid with this tree of 15 elements, so I could try again with, say, -4, and it's still like, nope, it's gotta be within 1 to 15, so I do 15, and as you expect, the 15th, the last one, is 99, which is great, wonderful. So if I look at main.cpp, here are the given numbers in a integer array. This is the structure for the node that has its value, its key, and then an address to a left node and a right node. This is, I will get to this in a second. I will focus first on creating the tree, which is actually down here. Make tree, it's a recursive function. I first call it by giving it 0 and then the size of the index -1 for the ending index. And then I give the full index size here, which is its full size, and then a reference to a node, which will start at the head, but then recursively go down to its smaller children. It will find the midpoint, and then basically it'll take the half of the starting index and the ending index. I add it to the starting index because when I start going into separate chunks, I need to find the difference correctly. So I have to add the starting index there. And then when I do, I use that midpoint and just steal it from given numbers and put it in the key for the current node. So when this runs first, it's going to find the middle. It's going to find the middle value, which is going to be 65. Yes, 65, which is right in the middle. That's going to be the head node. And then all the other nodes are going to be filling down. So the next one on the left is going to be 41, and the next one on the left is 17. The next one on the left is 6. And the right of 17 is 20. You get the idea. So, wonderful. And then just some checking to make sure that I don't, if the range gets too small, that means that we've reached a point where there are no more values to put into tinier nodes, so we stop making more children in that part of the tree. This runs the left side, and then this runs the right side, checking if it's greater than 0 or if it's less than the size of the array -1. And generates new nodes, very similar for each type, generates a new node address, and then attaches it to the left, and then makes the tree. And then it calls the make tree again, giving it now the starting for the left side, the starting index, but then it's ending at the midpoint, but still keeping track of the full size of the array, and then running the whole thing again on the left node. Same thing for the right node, except it's now going to the midpoint +1, and it goes to the ending index, keeping full size and going right. So this is segmenting basically segmenting the array in smaller and smaller segments, and I just grab the middle one each time, and that builds up the array. This is print tree. I initially wanted to print it vertically, but I found it was a lot easier to just print it sideways, and I'm like, you know what? Let's just do that. It just makes more sense to me to print it sideways. You basically do it in order traversal, but you keep track of the height of the a specific value, and then just add that many spaces so it's in the right column when you print the tree. So this is what I use the log for. This is why I import math, because I take the whole size of the array and do a logarithmic calculation of that, then add 2, and that tells me how many how high this tree is going to be. So neat property there. Value height, I use a get height method. I can scroll up to that. One of my helper methods. Get height. It'll take the current node, and then this is the element, the value of the element that it's trying to find. It's sort of like a search algorithm, and it'll return the height of that. So if this node does not exist, I return -1. So you've got a bad tree head right there. If you have found the element matches the key at that current node, then return the height. So, and then we also keep the height here, which we set to 0 initially, and then we keep passing it +1 when we go down recursively. And then we just traverse the tree, and if it's less than the element, we go. If the current key is less than the element, we go right, and if the current key is greater than the element, we will go left. We don't need if statement for that. We just check for the first if, and then keep going. So that's great. That's how you return the get height. So the head tree node would be at a 0 current height, but then we keep going down. We'll get to like 4. 3. So at max, we'll get to 3. The height will be 3 down there. Make tree. Back to make tree. We're good with make tree. Print tree. Print tree is great because you just use the get height there, and we call get height each time we have a different value. So we are traversing down the tree, and then we are passing the key to that current node, and so it's basically like a double traversal. So I guess 2 log n to grab it when we're printing the tree. And then I use this first space string to like say how far ahead I want it in the tree. So like the head node doesn't need any spaces, but the children of the head node need 1 space. The grandchildren need 2 spaces. So we just use a for loop for that. And then we pass it the first space, then the key, and then return character for the next element in that tree. And then so we are doing the printing in the middle, but above we are doing it in order traversal. So we first call it if there's a child node on the left, and we call it right. And if there's a child on the right, we call the right node at the end. So this happens in the middle of those, so it prints correctly. I do this little number here to give me the size of the given numbers. In case I wanted to change how many elements were in the array, I would use this. Determines the size automatically using the size of commands, which is great. This creates the tree head node. I create a pointer to it. And then this makes the tree using that pointer. And then this will print the tree after I make the tree, which is great. So here is where we grab the user input for the kth element. It'll say, oh yeah, it's been constructed. Please enter the kth element. And then I'm like, perfect, type it in. And then it'll make sure it's valid in this do while loop. When it is valid, I also do this little concatenation here, so the first one will be first, second one is second with the nd, and the third is third. But everything else is just a th. So that's just so it looks nice when you print it. And yeah, I call the get element at when I'm printing out the output. So that's when I use the get element at right there. Let me scroll up to get element at. So this will take a node. It'll take a index, which is the index that we're trying to grab. It's not the value of the element. It is the index of that element, so the second smallest. I create a queue. Very similar. I tried using a stack, but then I realized because I wanted to get everything out first in, first out, instead of first in, last out, I could just use a queue, which is great. Works great. And then I use a recursive helper function, add to stack, to populate the queue with an in-order traversal of everything. I'll go to that. So it takes the tree head, and it takes a reference to the queue, so that we don't have to, it's not like a global variable. I can just have it inside of get element at, which is great. And then it does an in-order traversal, very simple. Add to stack if there's a left node. If you're in the current node and there's no left element, if there's no left child, then you're going to push the element to the queue, which is great. And then we go to the right one if there's a right one. So in-order traversal, very, very simple. So now queue is filled up with the in-order traversal, and now we keep track of the current index. We're starting the current index at 1 because the user types in 1 for the first element. And then we do a while loop here until it's empty. And then we check if the current index matches the index that the user wants. So if they said they want the third, it starts at 1. We check by getting so if it is, we will then return the front value in the queue. So after we pop it off, that's just the current correct element. the correct element at that index right there, and we increment the index there. Very simple while loop there. Go through the whole thing. We can't find it, can't return a correct index. Well, bummer, that's a -1. So there we go. I don't think that'll happen because I make sure the user puts in something between 1 and 15 before it even gets the number. So that's great. Those are all of my functions. And I've explained everything. So yeah. And you can run it immediately by just doing a make run. So compiles everything, boom, just like that. And I say 89. Oh, sorry, I'm at 8. And 8th element is 65. Oh, look at that. That's the head of our node. Isn't that cool? So yeah, that is it for me.